All right, well, Happy New Year, everyone. Kind of hope this year is better than the last 2 years. This talk is a slightly expanded version of a talk I presented at the 2018 Rocky Mountain Section GSA meeting held in Flagstaff. That talk, unfortunately, had the same time slot as the Grand Canyon session. And in spite of the small crowd, which was about 5 or 6 people, including the folks running the session, the talk was, if I don't mind saying, a wild success. So when Mike asked me if I could put the talk together on some recent findings in the Proterozoic of Central Arizona, this talk came to mind. Much of the data presented here also came from a GSA lithosphere article published in 2020. My co-authors are Chris Daniel at Bucknell University in Pennsylvania, and James V. Jones III, he also goes by Jamie, who's with the USGS in Anchorage. Chris was the first author on the 2013 GSA paper defining the Picorous orogeny in north central New Mexico. And we'll come back to the Picorous orogeny a little bit further along in the talk. Jamie Jones has had a long history studying prominent quartzite successions in the Proterozoic Southwest, with several papers considering their provenance and evolution from the Detrital Zircon record. Many of the initial Detrital Zircon ages that we obtained in this study were processed and analyzed by Jamie at the Geological Survey of Denmark and Greenland, and with some assistance from Dirk Fry and Christine Thrain. And that said, many others and facilities had a hand in this study, which stemmed from my dissertation at Colorado School of Mines. This includes Bruce Truggill, my advisor at Colorado, Carl Karlstrom, my co-advisor at UNM. Carl also provided some funding for portions of the zircon analyses through an NSF grant. And then there's a few others that need some credit, including Mark Pekka at the Arizona Lasercron Center, who ran a sample from the Four Peaks Pellite, Victor Valencia at Zircon, who analyzed my Hopi Spring samples. And finally, a tip of the hat to my field assistants, Bob and Debbie Beecher and Todd Kay, who traipsed around the field with me quite a bit, carrying fairly heavy loads. In this particular slide where you see I'm sort of standing precariously on a block of quartzite, across the canyon you can see folds. These are folds that are developed in the quartzites that are interbedded with shales of the Maverick Shale located in Barnhart Canyon of the northern Mazatzal Mountains. I'm standing on a red member of the Mazatzal Peak quartzite, which is actually stratigraphically above the Maverick Shale. So it's a very complex structure in Barnhart Canyon. And if you ever have a chance to, if you're going to take a hike around the Mazatzals, choose Barnhart Canyon. It's really an entertaining place to see. And it's a great place for structural geology. And anyhow, all these structures that you see, all the folding across the canyon, are products of the Mazatzal Orogeny. And of course, the Mazatzal Mountains is the type area for the Mazatzal Orogeny. Well, the type area Mazatzal Orogeny for the last 40 years has been, the Mazatzal Orogeny for the last 40 years has been presented as an event that occurred between 1690 and 1650 million years. Now that's could be also read as 1.69 to 1.65 billion years, but we'll keep it in the thousands and hundreds. And more recently, the event was expanded by Ernie Dubendorfer to about 1580 million years, primarily based on timing relationships outside of Arizona. So today in this talk, I'm going to present data that shows deformation attributed to the Mazatzal Orogeny in the type area occurred between 1470 and 1380. Nearly 200 million years later. And that event was contemporaneous with the 1490 to 1380 Picorous orogeny described and reported in northern New Mexico's Picorous Mountains. Evidence supporting the revised timing of the Mazatzal Orogeny are based on correlative formations distributed over 3 areas of Tonto Basin in central Arizona. Mazatzal deformation involved the Paleoproterozoic Mazatzal group and erosional remnants of sediments that correlate to the early Mesoproterozoic Yankee Joe group with a maximum depositional age of about 1470 million years. And just to kind of give it in Grand Canyon terms, this is a stratigraphic succession that would occur somewhere between the Vishnu schist and the Grand Canyon supergroup. All the formations during the Mazatzal Orogeny were created through northwest directed contraction. The Mazatzal Orogeny generated an angular unconformity over which the middle Mesoproterozoic Apache group was deposited. And it's important to note that this revised timing, this 200 million year adjustment on the timing of the Mazatzal Orogeny, doesn't imply that there's any changes regarding observed or noted 1700 to 1580 million year deformation, or post or syntectonic plutonism or any volcanism that occurred around southwest Laurentian. It just skips over all that. Any deformation in that interim needs to be explained in a different way. This presentation refers a lot to the use of detrital zircon. Zircons grow in igneous environments where the crystals grow, generally recording cooling ages as the melt cools. Zircon can form from a fluton, or it can also be expelled during a volcanic event. And once it's exposed by weathering and erosion, these tough minerals enter the sediment record where they're transported into basins. And I'm using a thematic map over here in the right-hand corner, which is really looking at mineral types. But I think it's a nice proxy as to what detrital zircon ages might look like if you could see them moving through the sediment stream. So these zircons of various cooling ages are mixed in the transport, and they're basically recording local to regional provenance. They, of course, can be reintroduced into the sediment stream by repeatedly through various tectonic and erosional processes. And the samples collected from outcrops, for example, here's Bob Beecher collecting a Hudon quartzite. These samples are pulverized and crushed and then undergo a separation process, both by density and magnetically. Then once the grains are collected, the zircon is collected, it's mounted to a plate with standards, zircons that are used as standards. And then each individual zircon is targeted to look for a pattern, a growth pattern that's fairly regular. This is thought to represent an average cooling age of that zircon. When the zircon's blasted with the laser, it sends a gas stream, carries it down to a set of sensitive collectors that will count isotopic ratios in that zircon. These ratios are ultimately reduced to ages tied to the target spot on the zircon, thought to represent the main cooling age of that zircon. Finally, we take the data, all these zircons from that single sample, and we plot them in an isoplot with numbers, a number of zircon occurrences versus the age. In this case, we have 80 grains showing. We utilize only the grains that fall within 80 to 105% concordance. So in this particular plot, you see a bimodal distribution. This is very typical, say, of the Vishnu schist and the Grand Canyon. And you got population peaks of around 1822 and an Archean population peak of around 2635. So one thing to note that we'll be pointing to in this particular talk is that if you have a set of younger zircons or any other zircons that sit out here and create another nice shoulder or a peak out here, you can take that peak, and assuming there's enough zircons to make it statistically valid, we can count that peak as a maximum depositional age. In other words, if it's in the sediment, that sediment can't be any older than that age of that peak of zircons represented in that on the isoplot. We'll see a little bit more of this in the next slides. Just an overview of the Proterozoic overall in terms of the growth of the Laurentian continent. This is a map of North America. And essentially the basic story goes that the growth occurred from north to south. Initially around 2 billion years ago, we had amalgamation and clumping together, sort of joining together of Archean terrains and largely in the Canadian, the northern part of the United States. From there, we started there was a long-lived convergent margin that seemed to develop. And essentially, we can see these various accretionary terrains being grown out, including the Mojave, the Yavapai, Mazatzal, the southern and eastern granite rhyolite province, and then the Grenville terrains, all over a period between about 1.9 to 0.7 billion years ago. Arizona contains an excellent transect of 3 of these terrains. So getting a little bit closer, the map on the left is a regional map showing distribution of Precambrian rocks across the western United States. The map covers an area from Canada on the north to Mexico on the south. The states are all outlined by dotted lines. The Precambrian rocks are shown in gray all along and here along the Rocky Mountain uplift, as well as across the transect of Arizona and scattered throughout western and Arizona and eastern California. The black areas are 1.4 billion year old granites. And let's see what else. And then provinces are marked off or bounded by black lines. The red stars that we're showing on here represent sediments that contain detrital zircons with ages between 1600 and 1500 million years. And these are kind of unique because they don't occur very often in the rock record. In fact, up until about 10 years ago, zircon with cooling ages between these ages, 1600 to 1500 million years, were considered rare. The period of 1600 to 1500 was often referred to as a magmatic gap due to the fact that due to the paucity of igneous sources with similar cooling ages. We just didn't have any around to explain where these zircons were coming from. For example, on the north, you can see that we have the belt supergroup, which is rich in these magmatic gap ages. The only source that could potentially come from it would be the Priest River complex, but the extent of that complex is so small and the range of ages is so narrow that it's unlikely that it contributed to the belt supergroup. So there's been speculation that a lot of the zircon ages that have the 1600 to 1500 million year old age might have been derived from someplace like East Australia, like the Mount Isa region. Well, in the southern states, or the southwest part of Laurentia, we've discovered a number of these sediments. They're mostly erosional remnants or trapped within structures like a synform at Four Peaks, for example, or caught between the margin of a pluton. They also occur outside of Tonto Basin, including the McDowell Mountains. And what's more important is the work by Steve Skotnicki and Matisse van Soest have discovered that they've actually got tuffs and a pluton in the area, and probably have more that might act as actual sources for some of the zircon ages that we see in these essentially early Mesoproterozoic sediments. Further, we've also found some of these similar ages in quartzites that are exposed in the core of the Defiance uplift. And they've also been, of course, discovered in the Piedra Lumbre, which changed the entire story about the deformation of the Pickery Mountains from being Mazatzal deformation at 1650 to a newly recognized event at 1490 to 1380 that's been now named the Pickery Orogeny. The red outline that you can see on the map here corresponds to the Tonto Basin, which is shown in more detail on the on the right side of this slide. Tonto Basin is about 120 kilometers long. It's about 80 kilometers wide. Of course, it's occurring in the transition zone, which separates the relatively flat-lying rocks of the Colorado Plateau on the northeast from the extended terrains that we see for the basin and range off to the west and southwest in Arizona. The basin contains at the southern end of the Salt River, which drains into Roosevelt Lake, Tonto Creek, which comes down from the north and joins Roosevelt Lake, which then, of course, pours out into the lower Salt River Canyon. Major towns in the area would include Payson and Miami Globe, and I'm also going to refer to the town of Young because of its proximity to one of our samples that we've collected that helped constrain some of the early timing of the Mazatzal Orogeny. The next thing I want to show you is that we've got the primary areas we're going to look at are the Mazatzal Mountains, Four Peaks, and the Upper Salt River Canyon. The areas that are covered in blue represent a post-1700-year-old quartzite that's still Proterozoic. This would be the Mazatzal group, for example. This age quartzite can be found at Tonto Bridge, Christopher Mountain. It's the quartzite that makes up the Four Peaks. And it's also found in the White Ledge Formation, which runs along for 14 or up to 16 kilometers along the Upper Salt River Canyon. And then there's in green, these green lines show the occurrence of pre-1700 quartzites that occur along the Slate Creek Shear Zone, which transects the northern third or two-thirds, or the northern third of the of Tonto Basin. And finally, just a little bit more background. The person that originally did the first mapping in the Mazatzal Mountains was Elder Dewey Wilson. Wilson received his BS in economic geology from Missouri School of Mines and Metallurgy in 1914, and soon found himself in Arizona, where he got a job with the Arizona Bureau of Mines, which is Arizona Geological Survey today, working as a geological technician. While he was there, he decided to attend the U of A, and where he worked on his master's thesis. His master's thesis focused on quartzites in the northern Mazatzal Mountains that had been pointed out to him by Leslie Ransom's work in Darton. He described the quartzites of the Mazatzal Mountains, but he also located similar looking quartzites in the Del Rio area up near Prescott. And then subsequently compared the quartzites to other quartzites around the state, such as quartzites in the Grand Canyon, as well as the quartzites in the core of the Defiance Uplift, and quartzite up in the Wasatch Mountains of Utah. Once he finished his master's thesis in 1922, he continued working as a geologist for the Arizona Bureau of Mines until about 1932, and then he decided to go off for a PhD at Harvard. And his dissertation basically expanded on the work that he did for his master's thesis, and basically looked into more detailed mapping across the Mazatzal Mountains, Four Peaks, basically across the state. The key thing that came out of his mapping from the work that he saw, he had recognized a lot of thrusting, for example, in the northern Mazatzal Mountains. We'll see this diagram a little bit sooner, but you can actually see layers in this rock that are warping up. They're being thrust up and over other quartzite members in here. And based on the mapping, the deformation that he saw, he concluded that after deposition of the Mazatzal quartzite, and long before the Apache sedimentation, the region had undergone some profound crustal disturbance that he termed the Mazatzal Revolution. And he saw this as a major regional event. Just to give you an example of the quality of his mapping, on the left is a mapping from his dissertation, his 1937 dissertation from Harvard, versus mapping that's a compilation of mapping by myself, David Pools and Carlstrom, Rucky and Conway's wilderness mapping, Michael Pendergrass, and Wilson's mapping, of course. And there's quite a similarity in the style and the quality of the maps. And since we're looking at the maps, I'd like to introduce you to the basic stratigraphy of the Mazatzal group, which is sort of the focus of this talk. In the Mazatzal Mountains, we have the Mazatzal group rests unconformably over two different units. That includes the Payson ophiolite, which is a unit that's as old as 1729, sheeted dike complexes and turbidites. And on the other side, there's apparently a large normal fault And we'll talk about this in a little bit, but the upper Alder group is exposed on the other half of the Mazatzal Mountains, kind of the southern part of the range. The basal part of the Mazatzal group is the Dead Man Quartzite. It's overlain by the Maverick Shale, which includes some of those quartzites that we saw in the previous slide, in the opening slide. And then a thick section of Mazatzal Peak quartzite. And then overlying that is our erosional remnants of a shale called the Hopi Spring Shale. Earlier mapping thought that this shale might have been a thrust repeated Maverick Shale from below, possibly being like a roof thrust over the top of the range. However, the detrital zircons from that yielded a maximum depositional age of 1570, suggesting that these, supporting the fact that that is actually a unit that's stratigraphically above the Mazatzal Peak quartzite. And then on the lower right-hand corner is a balanced cross section through the transect shown on the map. And that section restores to about 35% shortening. And this particular restoration, I use Midland Valley software. And in this particular interpretation, I've shown that there could be a possibility that we had some syntectonic growth on an underlying basement fault within the range. This basement fault would be the structure underlying the area around Barnhart Canyon, which causes some of the complex deformation that you see there. And then finally, the Proterozoic stratigraphy of northern Tonto Basin. It's about 12, at a minimum, 12 kilometers thick. And the Mazatzal group, which you just described, occurs right at the very top, along with the shale at Hopi Springs. And then it's overlain only in the southern parts of Tonto Basin by the Apache group. But underlying it, it includes the Payson ophiolite, which is an incomplete sequence of ophiolitic sequence that was described by Jesse Dan. And then overlying that is the East Verde River Formation, and it appears to be an unconformable contact between the two. The East Verde River Formation is mostly a lot of interbedded or turbidite sequences, thick sequences of turbidites. And it's got an ash that was dated by Dan of 1720 in the middle. And finally, unconformably overlying the East Verde River Formation is the Breadpan, Flying W, and Red Rock group, which is a combination of rhyolitic volcanics and such. And then overlying that unconformably is the Houdon Formation, which may also be called the Pine Creek Conglomerate, based on my work. And then there's another unit called the Board Cabin that isn't shown in here. But overlying all of that is the Hagler rhyolite, which yields a date of about 1702. And a lot of earlier workers looked at these rhyolites, especially in places where they thought that the Houdon Formation was the Mazatzal Peak quartzite. And so there was an assumption that the Mazatzal Peak or the Mazatzal quartzite to the Mazatzal group is deposited around 1700 million years. And of course, all these earlier unconformities suggest that there's multiple periods of pre-1700 tectonism going on. And of course, rhyolitic volcanism appears to be associated with some sort of extensional tectonism going on between 1710 and 1700 million years. So the focus of the talk is really the definition of the Mazatzal Orogeny. It occurred after deposition of the Mazatzal quartzite and long before Apache sedimentation. And it was termed the Mazatzal Revolution. Well, Lee Silver came in when he had his new uranium lead dating techniques and basically recognized that the Mazatzal Revolution is the same as the Mazatzal Orogeny as it was defined by Wilson. And he decided to come out and based on the mapping that was existing at that time, took a sample of red rock rhyolite, which occurs back over in this area, and obtained an age of about 1715. But to find a cross-cutting relationship, there was no other cross-cutting relations for datable material in the Mazatzal group. So that forced him out into the basin, out towards Young, Arizona, where he sampled the post-tectonic granite near Young, which yielded an age of 1650 million years. And the assumption at that time was that the deformation that he saw in Tonto Basin in the pre-1700 strata it also included the deformation that was associated with the folding and thrusting attributed to the Mazatzal Orogeny. Alternatively, Livingston in 1969 reviewed Wilson's work and recognized that the Upper Salt River Canyon had all the elements which fit the description of the Mazatzal revolution of Wilson. In other words, it had the Mazatzal quartzites, and it also had the Apache group resting over it. Furthermore, it also had a granite that intruded the deformed stratigraphic section in the Upper Salt River Canyon. And based on that, based on the underlying age of the underlying volcanic unit below the quartzites and shales equivalent to the Mazatzal group, he determined that that the Mazatzal orogeny occurred between 1425 and 1380, plus or minus 100 million years. And that was the large error was mostly because of the method he used, which was rubidium strontium. But once that deformation occurred in the Salt River Canyon, you have these very high angle beds that are overlaid by nearly horizontal, even today, Apache group that basically onlap this expression of high topography formed by at the angular unconformity. But because he used rubidium strontium, it kind of got looked over and bypassed as a valid or a reasonable technique. And so the next group of people that came in the 80s and the 90s included Carl Karlstrom, who surmised that the Mazatzal orogeny kind of came in on the heels of the Yavapai orogeny, which he believed had the Yavapai orogeny was active around 1700 million years based on crazy basin quartz monzonite over near Cleator, which was a syntectonic intrusion along the Shylock shear zone. So he surmises the Mazatzal orogeny had to happen sometime after that, and that it had to be over by about 1650, which is the age of the young granite near, that was the same one that was sampled by Silver, but he resampled it and had it dated by Samp Bowering, which got the 1650 age again. But the only difference is where they sampled it, it was actually intruding folded beds of alder group as well. And so the assumption there was that this intrusion, post-tectonic intrusion into the folded beds of the alder group included deformation in the Barnhart above the, in the Mazatzal group. So what the problem is that there's this angular unconformity all along the base of the Mazatzal group, all across the entire range. And this is what you see in this sort of diagrammatic, shown as a diagram. And actually at the base of this, at this unconformity, there's a rhyolite just below the dead man quartzite, which yields a date of about 1701. It also occurs over a Tonto Bridge. Furthermore, the quartzite that's underneath it has an angular relationship underneath the Mazatzal group as well. So this is the east face of the northern Mazatzal Mountains. These are the thrusts that you can see across the area. Cactus Ridge is on the far left. Mazatzal Peak and Suicide Ridge is just to the south of Barnhart Canyon, which is where you saw the folds in the opening slide. This area is very complex because there's an underlying large normal fault or apparent normal fault that may have as much as 8 kilometers of throw on it. It basically juxtaposes upper alder group against sheeted dikes of the Payson ophiolite. And so these thrusts, it gets very complex where it tries to get up and over this basement high, but then it accumulates into a single thrust called the Barnhart thrust. And then of course we have additional thrusts like the Rock Creek and the North Peak thrust. And if this is a true foreland thrust belt, most of these thrusts occur in a forward propagating manner. So the North Peak thrust would be one of the youngest thrusts. And just to take note as well that underneath the Barnhart thrust are folded sediments of the Hopi Spring Shale, which is where which yielded a 1580 Detrital Zircon peak, which constrains its age to a maximum of 1,570 years or 1,700 million years. So it's an important point to note, and we'll talk about it in a second. Just one more run at just showing you a little bit of the geology around the Tonto Basin. This is from the first place we're going to look at is Barnhart Canyon again, up in the northern Mazatzal Mountains. This is a 2 meter, in the upper right-hand corner is a 2 meter thick quartzite. And when you restore this quartzite, it restores to about 35% shortening, which is what the regional balance section shows as well. But we know that most of these beds, the deformation in these rocks is in a brittle ductile transition. So you needed something above the range in order to get a lot more thickness to get these rocks to depth so that they would deform in a ductile manner. And that's really where you'd want a roof thrust. So in addition to the 35% shortening, if we added a roof thrust over the entire mountain range, that would increase the thrusting overall to about 55% shortening, which is more typical of thrust belts around the world. Across the canyon, oh, and one other thing, I'm not sure if any of you have noticed, but I'm standing in the middle of the quartzite, kind of as a scale, right here in the purple jacket, just to give you a sense of size, scale on that thing. And the photograph down below, which was taken by Bob Beecher, is there were a series of thrusts up in the Mazatzal Peak quartzite as you come up that formed a series of different ledges. And along parts of the ledges, it's really hard to tell that you've got a thrust. It's only when places where the thrust actually starts to ramp up. In this case, this is in the red member of the Mazatzal Peak quartzite. That's obvious that these thrusts are present. And there's several of them up through the section that thicken the entire quartzite package in Barnhart Canyon. And of course, you've got these spectacular footwall folds, but remarkably, there's no folding really shown in the hanging wall block, no corresponding hanging wall fold shown here. The next place we'll look is just the Four Peaks. So most of you are familiar with Four Peaks. I'm sure you've seen it when you look east from Phoenix. It's pretty prominent, but this is what Four Peaks looks like from the east. In the foreground is the White Ledge Formation in the Upper Salt River Canyon. So the Upper Salt River Canyon is just due east of Four Peaks. The topography of Four Peaks is formed by these resistant ridges of quartzite. And mapping of Four Peaks is showing that it's a northwest vergent sin form, and it's also inwardly plunging. And in the core of that sin form is a pellite. And Estrada, a student at ASU, worked on his master's thesis in the area. And when he described the section in here, he described, of course, the Four Peaks quartzite, but then he found the pellite in here. And it was his opinion at the time that the pellite was also stratigraphically above the quartzite. And again, when I sampled from, the shale from this section, it yielded a maximum depositional age of about 1580. So basically the story here is you can't form the fold until only after the 1580 shale is emplaced. And then finally, the Upper Salt River Canyon. If you haven't had a chance to visit the Upper Salt River Canyon, and I'm not talking about where Highway 60 crosses the canyon, but go down somewhere in the middle, like Clay Spring, just above Quartzite Falls. You get these spectacular flat irons of quartzite exposed with the Salt River winding its way through. This particular shot is just above, looking at the quartzites of the White Ledge Formation and the lower part of the Yankee Joe group, or called the Yankee Joe Shale. Just around this corner is a location of what used to be a very dangerous rapid called Quartzite Falls, which was literally a pour over. You can imagine this white quartzite bed extending across the canyon and the river pouring over it. They made a perfect keeper. And so that when you came around in a river trip, it was sort of frightening because your pullout was just above those falls. And then you had to actually take the boat apart and portage it over to get it past the falls. You could try to line your boat through, but the keeper was so perfect, it would just maul your boat if you tried to pass it through. Well, in the 1990s, some commercial boatmen came in there, and because of some people who had died in the area, they decided to go ahead and take the incentive to go out and blow up the falls. It was completely illegal, and they did get caught. They left plenty of evidence. But in any case, it's a spectacular place. These beds are dipping at about 56 degrees, 55 degrees. The White Ledge Formation, of course, is resting on the Redmond Formation back here, which is dated at 1657. And the lower picture on the lower right is Bob Beecher standing in on one layer of the White Ledge Formation with a nice exposure of trough cross beds and ripple bedding. All these sedimentary features are just prevalent throughout the quartzite. It's a spectacular area to look. And then there's undulations in here that are sort of kink folds and kink bands across the quartzite through the deformation. So we described I described the Mazatzal group earlier, the Deadman, Maverick Shale, Mazatzal Peak quartzite. And what I want to do now is take a look at a panel of sections or strat columns across the Tonto Basin. And I'll show you my interpretation of what I think is going on. In the northern Mazatzal Mountains, we've got the Mazatzal Peak quartzite and well, the Mazatzal group itself with this shale that resting on top. Now the shale is shown as with an unconformity in there, but it's really kind of a disconformity. The contact looks quite conformable. I think we can correlate that to this pellite, which is in the core of the fold at Four Peaks, which yielded a date of 1580. And then in the Upper Salt River Canyon, this section is about 2 kilometers thick. It's well preserved, but it is encased in the Rune granite, which intrudes the section. But the youngest age we're able to derive from that particular section is 1471 for a maximum depositional age before it was formed. And then of course, we've got a large number of ages all through the section as well. So we'll go just one by one just to show you examples of what each looks like in terms of evidence. So this is the Hopi Spring Shale. These are folds of the Hopi Spring Shale occurring just beneath the Barnhart Thrust. I collected the sample just above the Continental Divide Trail, which is right here. You can see the folds are vergent towards the northwest, and strongly folded. And in that sample, we've got we're able to measure 160 grains. And we, of course, got a nice broad range of ages, including 1733 peak population ages. But the thing I want to draw your attention to is this small shoulder of ages over here, which yield a statistically significant grouping of 1571 million years. So that constrains the age of the maximum depositional age of these, of the shale here. The next location is a sample collected out of the synform at Four Peaks. Again, we have 93 measurements. And again, we got a very strong peak of ages around 1580, which again, it's pretty tough to explain how these shales got in here other than depositing them before the synform was folded. And then finally, in the Upper Salt River Canyon, this is a full view of the entire stratigraphic sequence that we see in the Upper Salt River Canyon. We have on the left, the Redmond Formation, which has a date of 1657, just beneath the White Ledge Formation. Then we have the White Ledge Formation. Of course, the White Ledge is very prominent here. And then the contact with the Yankee Joe Formation, which appears conformable over the entire distance, 14-kilometer distance. What's also important to note too is that the White Ledge Formation is about 100 feet thick at the far end here, but by the time you get to the 14 kilometers to the west, it's over 800 feet thick. So there was some active tectonics going on where these sediments were filling in a basin. And of course, the trough crossroads we saw on the previous slide do record on if you restore the bedding to flat, a westerly paleocurrent direction. Then we have the Yankee Joe Formation, which has got ash layers in the lower section and then which we've collected samples and additional detrital zircon samples, which give us maximum depositional ages of around 1490. And then from the top of the Blackjack Mountains is the Blackjack Formation, which yielded a 1471 maximum million-year depositional age. And then the whole section is intruded by the Rune granite, which has got a new date of 1444 that was determined by Chris Daniel and was presented in our GSA field trip guidebook. And finally, just to show you, these are some ash layers that are in the that I want to compare. The ash layer on the left is from the Lower Yankee Joe, and we yielded an age of about 1505, plus or minus 6 million years. The ash layer on the left that you see is from the Piedra Lumbre in the Pickery Mountains. It yields a layer of 1503, plus or minus 6. These two ash layers are all almost 560 kilometers apart, linear distance. And they're very similar. There are additional layers above and below that contain ages up into the 1520s and down into the 1490s. Anyhow, it was these ash layers in the Piedra Lumbre that was a clue to Chris Daniel that deformation was not 1650 deformation as presented before, and rather this 1490 to 1380 deformation. His work also includes a lot of barometric temperature and barometric pressure data to show that this section was rapidly buried to 10 kilometers depth before being exhumed. And then finally, just to talk a little bit about how we got the earlier ages and what our limitations were, which led to these earlier age constraints that we tried to give for the Mazatzal orogeny. First of all, we didn't have rapid dating techniques like we do today that allow us to do detrital zircons. We scoured the entire Mazatzal group looking for ash layers or anything we could date and to no avail. So our next best guess, or not next best cross-cutting relationship really was this post-tectonic granite near Young, Arizona. Now, one of Mike Williams' students, Calvin Mako, came out and collected a sample here, and that sample yielded an age of, using LAICPMS methods, of an age of about 1664 plus or minus 20. So the problem is when we dated out here, there was this assumption that the deformation along the Slate Creek Shear Zone, these folds and so forth that occur along here, basically were included with the folding and thrusting that we see in the northern Mazatzal Mountains. And it just doesn't seem to be the case. And that's what's shown by the Hopi Spring Shale, the age of the Hopi Spring Shale, and all the units at Four Peaks and at the Upper Salt River Canyon. So without recognizing the significance of that D2 unconformity, we were forced to estimate the timing of the Mazatzal orogeny as much earlier. And finally, it's just another look. It's sort of a simplified cross section to the Mazatzal Mountains and the Slate Creek shear zone. The Mazatzal group post 1700 units are shown in blue. Pre-1700 are basically shown in the tan. And essentially, we just didn't involve anything to do with the Mazatzal group itself. Everything was, all the estimates of the early estimates of the Mazatzal timing were based on pre-1700 rocks and the post-tectonic young granite. So basically what we've done is we've collected the youngest sediments involved in deformation to constrain the age of the Mazatzal orogeny. So anyhow, just in summary, the timing of the Mazatzal orogeny is, we think, is roughly between 1470 to 1444 when the Rune granite intruded, but the Rune granite is also probably a syntectonic deposit. And there's areas that have been shown that include shear zones through the Rune granite. So in reality, it's probably, we can easily extend it to 1380 if you assume that at 1444, these rocks were at depth, 6 to 8 kilometers deep, and then they had to be brought up to the surface to be exposed, both the ruined granite and the quartzites and shales, so that the Apache group could be deposited over the angular unconformity around 1340 to 1320 million years. And our early constraints timing on the Mazatzal Orogeny were based on cross-cutting relationships, or were in the pre-1700 million year old rocks. And unfortunately, we made an assumption that the deformation below the D2 unconformity included the deformation above. And that's my talk. If you can open it up to any questions.
Excellent, Mike. That was great. The field shots were absolutely spectacular. Does anyone have any questions at this point for Mike regarding the Mazatzal and the timing?
The mother lot is great size hole that reach access and views, but our biggest concern is that it needs a lot of updating. Yeah, I don't know that we've got the time to give up in order to make this the house of our dreams.
I'm sorry, somebody's busting in on this. Is there a question in there? Were you trying to get a hold of Mike and ask a question?
I was just going to thank him for a really great presentation. You made some pretty good sense out of it for an old worn out engineer. Thank you, Mike.
Thank you. Welcome.
Yeah, I agree. It was an excellent presentation and very illuminating for me. And of course, I don't have a lot of background in the Proterozoic, so a lot of this was relatively new to me. What is this? Is this standing as with the other folks have accepted basically the premise and the age dates and this concept of the new aging for the Mazatzal?
Yeah, basically the Mazatzal Orogeny is contemporaneous with what we know with the Picorous Orogeny.
Mm-hmm.
Most people seem to accept it with no problem. It's one person in particular that doesn't like it, and basically he's told me that under any circumstance will he ever accept that the Mazatzal Orogeny is anything other than 1650, around 1650 million years. And part of the problem was when the Mazatzal Orogeny was originally defined, the early constraints were given, a lot of work moved out of the state. And so areas in New Mexico and Wyoming, anytime you saw deformation that was, say, after 1685 was immediately attributed to a 1650 Mazatzal Orogeny. And that included the Pickery Mountains. And again, when Chris, we made these discoveries in 2012, or that's when our paper came out. And Chris had come up with these dates, similar dates at that same time. And so he was able to get ahead and get that paper out, which was really great because not only does he include the ages, but he also includes thermobarometry to actually show what the sediment pile did and how quickly it was buried. So, but this is a big event, and there's a lot of I hear arguments, particularly from one party, about this evidence and evidence in shear zones at 1650. Well, I don't argue that there might be evidence of deformation in the shear zones, but what you see in a shear zone, if it's a major event, should have an angular unconformity somewheres. And that's why it's important to understand that. The other thing I think is important about this talk, and what we found is that this is a stratigraphic package. It was nearly lost to erosion. It was nearly lost because of the Mazatzal Orogeny, and that it could have also been completely erased during the Mogollon Highlands uplift during the Laramide. And what we see, though, is little tiny patches of it all around the state, including the core of the Defiance uplift in the Four Corners region. And if you take a look I recommend everybody take a look at the paper by Jamie Jones in 2015, where we propose that it's possible if you take all the zircons from the Upper Salt River Canyon, Detrital Zircon records, and you overlay them with the Detrital Zircon records for the entire belt supergroup, there's a really good argument that suggests that the unroofing of Laurentia between 1470 and 1380 was the filling of the belt supergroup. And the belt supergroup actually has lava flows internally that you can get dates from, as well as the detrital zircon record. So it's Jim Seedor, Jim Sears at one point had predicted there was a basin that covered all the way across in the belt supergroup, all the way across into Arizona, but we never had the evidence. And now it looks like we might have some of that evidence. And who knows, maybe somewhere in the Grand Canyon, resting on top of the Vishnu schist, is a little bit of quartzite, just like the quartzite at the core of the, that's in, that we see in Blue Canyon and the Defiance uplift. So, but anyhow, it just means a lot. It puts a lot of focus back on what's happening in the Yavapai orogeny. When does that actually end? And what happens during this apparent quiescent period between 1660 and the actual Mazatzal Orogeny at 1470 to 1380.
Hey, Mike, you have there's a question from, hang on just one moment. It's moved down in the chat and I'm not fast enough to get back to it. Jeff Myers asked, do you know how your rocks relate to a quartzite located just north of Chino Valley, which is of similar age? It originally was considered Mazatzal quartzite equivalent, but then was thought to not be due to too young of an age.
Can you tell me how young of an age? I mean, what does he mean?
Jeff Meyer made this comment. I don't know.
Yeah, I don't know specifically. Part of my dissertation looked at sediments all the way across the state. And so from as far north in the northwest as the Cottonwood Cliffs, or no, it's a Grand Wash Cliffs area, the Wallapais, used a sample from Jerome Canyon that John Spencer collected all the way across. And that's an entirely different talk.
Yeah.
That paper's been kind of hung up because of this timing of the Mazatzal orogeny argument that I'm making. But I have been doing a lot of work on that stuff. I did present a poster at GSA in Phoenix that looks at detrital zircons and compares the populations using multidimensional analysis. So if he wants to talk to me offline, he can drop me a line.
Yeah. Okay. And the Arizona Geological Society has to thank you, Mike, because Elizabeth Potteroff says, thank you all. It's nice to find real geology. I will join and hope to meet you in person someday.
Oh, that'd be great.
Yep.
Yeah, it'd be nice. Maybe we could put together a field trip, maybe repeat the field trip we did at GSA.
Yeah.
It was really nice.
And we've got among our new officers, we've got some real interest in developing some new field trips, and they've got one or two already set out, I think, for this next year. Omicron, if we get past the pandemic.
Yeah.
So it'd be really great. Let me see if there's any further questions in the chat. And to all of you, I was remiss. I should have pointed out that Mike Doe is an affiliate with the Arizona Geological Survey and has been for the past 3 years or so. Somebody said Del Rio quartzite, which is up in the Prescott area. So maybe that's quartzite he was referring to.
It might be. John Spencer did some really nice work up there.
Yeah.
On the Del Rio quartzite.
Yeah.
Hopefully we'll get a chance to look more at these basins, at the basin story, because there's some really interesting results from it. Not necessarily the Del Rio quartzite, but other metasediments around the area. When you comparing everything from the Vishnu schist all the way down through, there's a very systematic story that's going on there that's illuminated by multidimensional scaling in terms of showing how populations, it basically compares age populations and places them in the Euclidean space. So you can sort of see them in terms of relative positions, in terms of similarities. So that's a pretty cool technique out there.
Hey, Mike, you have another question from Tim Lawton, and he's questioning the possible sources of the volcanic tuffs that date to 1503 million years. Any sense of that?
Well, yeah, Steve Scott-Nicky has been working. He did a really nice map of the McDowells,
Right.
And in that part of that study, they collected a couple samples, and I think they collected several others, but at least two of them were published in his field guide to the McDowell Mountains. And one of them was 1544 out of the Taliesin Tuff, and then a granite with an age of Antigua called the Antigua granite, which has got an age of 1525. So it's really possible that there's something going on over there that other source rocks that they haven't published yet that might explain the 1503, or 1503, 1505 age. But it's really interesting because it covers such a broad area, and it's quite possible that this Hopi Springs Shale, for example, may have been a foreland deposit developing ahead of a loading crust as this oncoming Mazatzal Orogeny occurred. And we may have had volcanism going on, kicking off somewheres. The other thing I didn't really mention before is, but the northeast trend that you see in the Paleoproterozoic, the Mojave, Yavapai, and Mazatzal, they all extend across North America, and they're found in the Baltic regions, across in Europe, and they're also found across in Australia. And so there's a lot of potential connections in there. And these new magmatic gap ages are popping up in a lot of weird places like Southeast China. My work has been cited on guys looking at stuff there. But there's also a series of dikes out of Australia that they're finding up in the Northwest Territories that also connect back to similar dikes in Australia. So it's an evolving story, and I think it's going to have a lot to do with what we see in Arizona, because a lot of the Arizona mineral deposits, for example, I think are fundamentally controlled by basement, Proterozoic basement structures. And we need to pay more attention to that. And so the understanding more about the Proterozoic basement may give us some insight into why we have mineral concentration, say along the Globe Miami or the Miami Superior Trend, for example. That's the division between continental deposits sorted to the north and more offshore type deposits in the Proterozoic, what we call the Pinal schist, which is really a misnomer for a very complex mixture of lithologies.
Yeah. Mike, you have two more questions, I think. And this one is it possible to test trace element concentrations of various zircons to differentiate the various bits of Proterozoic crust they represent?
I think so. We wrote a paper in 2013 about, we were utilizing Detrital Zircon and epsilon hafnium as combinations of isotopes to try to fingerprint source regions or type areas. There has been some work that's been done by, headed up by Gashnig at Lowell University, I think it is, in Pennsylvania. I'm drawing a blank on the name. But he's had some students that have been working on using multiple types of isotopes. These zircons have a lot of different isotopes that could be used. And so there may be some way to kind of isolate some of the sources of these zircons. In other words, fingerprint it right back to a particular source to try to get a better idea of where it came from. But at this point, it's an evolving technique. Every year we get better and better dating techniques, better techniques with the lasercron, and capabilities of doing multiple gases. You carry multiple isotopes across the stream to the multi-collectors. So I'm super excited. This is a revolutionary time to be in geology in terms of geochronology.
There's another question from Tim Lawton. I think maybe he's talking about the Del Real quartzites. So the question is, so why are these things all quartzites? Was the weathering intense? And that was something that I think John Spencer was trying to address for Del Real.
Yeah, and that's been addressed over a number of times. There were papers, some discussions back in the 1980s with Clay Conway and others discussing, and Rona Cox discussing how much rhyolite you would need to weather to make, say, a kilometer of quartzite, if that was possible. Yeah, it looks like the weathering regimes are pretty aggressive. And in fact, the overall Mazatzal group matures up section. And so when you get to the top of the Mazatzal Peak quartzite, say in the northern Mazatzal Mountains, it's really silicious. Just some few red cherts left over in there that were probably derived most likely derived from the Yavapai terrain to the north. When you actually get down to the White Ledge and the White Ledge Formation, that's a pure orthoquartzite. It's got nothing in it but well-rounded grains, including the zircons, which was amazing. It yielded these super round, polished zircons, which with ages, when you look at the detrital record of the White Ledge Formation, and you look at it on an isoplot, it looks very much like the Grand Canyon Vishnu schist. Part of that might be is that by the time you got to the White Ledge being deposited, perhaps a shoreline deposit, it was seeing a very cosmopolitan view of the zircon populations across Laurentia. It was it must have been quite flat and could see a much broader area. But it has zircons up to 3.2 billion years old in it.
Okay. That's all the questions that I see on the chat, unless somebody wants to toss something out, and feel free to unmute yourself if you like. I think you can do that.
And please, if you have anything that you're interested in terms of the Proterozoic, or maybe even have a student that's got an idea or want to send out, there's plenty of work to do in the Arizona's Proterozoic.
Yeah.
A lot of stuff that needs to be revisited that that could really benefit from the new techniques that are available. I mean, just between the time I did my master's thesis and my dissertation, I went from working off of brown line mylars that took 2 or 3 months to make, to suddenly having satellite imagery and a drone that could make my own base maps, or photogrammetry, or topo maps, and everything's on GIS. It's amazing, and so there's a lot to be really exciting times in my mind for geology.
Well, I think you were right about the Pinel schist. It would be wonderful, I suppose, for people to go in, somebody to go in and revisit that. I think you were on the field trip with us at one time, and it was everything. It was amazing how diverse the rocks, the lithologies were in the Pinel schist. It was just almost incomprehensible how very were.
Yeah, we owe a lot to Aaron
Yeah.
Mayer. He's really, and he's still doing it. He's just out there pounding dirt and collecting samples and doing tabletop processing at his house just to keep his costs down. But he's, this is a guy, if you're talking about passion in geology, this is a guy that's got it.
Yep.
So, and I was recently out mapping with Clay Conway, who mapped out there back in the 1980s and 70s through 90s. And he's come back out and trying to finish up papers that he couldn't finish when he was at the GS.
Mhm.
So,
Very good.
Yeah. Hey, Mike, I have a couple questions.
sure.
Sure.
The first one is, what is your interpretation of the tectonic setting for the Mazatzal Orogeny? Because you're dating it much later, it's not really part of the, let's say, the crustal forming deformations of 1650, 1700 and later.
Yeah, that's a really good question. Exactly what drives the Mazatzal Picaris orogeny, I'll combine the two because they have the same timing, is uncertain. It must have been something fairly big, but we don't know yet. I don't think there's been any conclusion. Is it simply a matter of changing the angle on a subducting slab somewhere to the south, present day south, or not? In terms of the earlier times, when does the Yavapai, the Yavapai orogeny, for example, is characterized as really a series of orogenic events that probably occurred from 1740 to at least to 1700, which is, roughly the age of the deformation going on around the Crazy Basin quartz diorite, quartz monzonite, I'm sorry, over near Cleator and along the Shylock shear zone. But if you can move the Mazatzal orogeny now out of the way, put it at 1470 to 1380, then you can actually maybe more reasonably extend the Yavapai orogeny to say around 1760, 1765, which is the age of the post-tectonic young granite, or granite near young. That said, you still have Plutonism. Now, Aaron Mayer has suggested or proposed that there was a spreading ridge subduction event that may have occurred around that time. And if you imagine a spreading ridge going under, the backside is probably going to be fairly passive once that plate has gone down. Yet you'd still have plutonism at that time, which would be the granite near Young, this post-tectonic granites. And it wouldn't be until the Mazatzal Orogeny later on that would actually uplift and expose the Mazatzal, the granite near Young to its present configuration along the Slate Creek shear zone. So, but what's going on between, I don't know. We see a lot of, the Mazatzal group doesn't indicate any sense of real tectonism. It's just getting more and more mature up section, as if you're just reworking sediments over and over. However, in other places like in northern Wyoming or southern Wyoming, you've got the 1580, Dave Jones, I believe it is, came up with the 1580 age of coming out of some zircons and a shear zone up there. There's the Monzanos have some 1650-ish ages going on there. But they're all in these little shear zones. And so, I come from the oil industry where we consider active stress regions and what controls fracture development and things of that sort. And one of the concepts out there that Zoback has come up with is, you've got this brittle crust, and the brittle crust is usually critically stressed at all times because you've got this lower ductile crust. And I often wonder if is it possible that some of these shear zones that we're seeing these 1650 deformations, but no regional unconformities around them associated with them, that maybe these shear zones are just accommodating stress releases of the overlying brittle crust, perhaps. I don't know. But right now, I don't see any, from 1760 on, I just don't see a lot of tectonism evident, certainly in the stratigraphic story. So it could be just a long period of quiescence, and then there was some sort of plate reorganization or collision of some terrain from the south, maybe sort of like South America during the Ouachita Marathon orogeny that plows into the crust and then breaks off and backs off or something. I don't know. Any feedback, or do you have any insight in it yourself?
No, not really. I'm not even a professional geologist. I'm just very curious.
Oh, it's a great question, though. Yeah, thanks.
Yeah, my second question is a little bit more narrow, and that is, in your map, you showed some similar quartzites, let's say in the Hagler Creek area. You mentioned Christopher Mountain.
Yeah.
I think McDonald Mountain east of Gisela also has quartzites that might be related. Have you done any sampling of those in, let's say, that part of the Tana Basin?
Yeah, I sampled some quartzite over by, it's called Sheep Basin Mountain.
Yeah.
This is, there's McDonald Mountain, which was mapped by Sean Sherlock. I'm trying to recall if I collected a sample there. I don't remember offhand. Most of those samples yield, what they yield is they're very unimodal. They yield very narrow ranges of zircon ages, which are ages that are similar to what you see in the Yavapai terrain, which is ages between 1740 and 1725 or so. And it yields these really narrow peaks. Now, what I did notice is that, for example, in the East Verde River Formation, there were these very narrow unimodal peaks. That's all you saw from your zircon ages. But if you got when you got into the Alder, you'd see that same narrow unimodal peak, but then there would be these little peaks of Archean ages popping up, as if you're getting some of these 2.6, 2.8 age zircons somehow floating into the system. And then by the time you get into the Mazatzal group, they get a little more prevalent. But it's a hard call in that respect. What really stood out in terms of timing of the Mazatzal orogeny was that you got this big gap, significant gap between the ages of these unimodal peaks that you see typical of the Yavapai terrain versus these new ages that are spread out that seem to reflect the typical of the Hopi Springs and the Pelite, and especially in the Yankee Joe group, which is in the Salt River Canyon.
So then do you think those quartzites even correlate with the Mazatzal quartzite?
No, I think they're Hudon. I think they're below it. And the reason I think that is mapping in Sheep Basin Mountain by Tim Brady, he recognized, he calls what he called a cauldron, but essentially the section is invaded by a rhyolite, which is probably the Hagler rhyolite. We've got very few dates out of there. What dates that we do have out of that area are not documented, not even a dot on the map, yet alone anything about their analytical results. A lot of those were Lee Silver ages, some are Sam Bowering ages, but for some reason at the time, just what we consider standard sampling methods today just weren't being carried out. But anyhow, if you go to the mouth of Shake Tree Canyon, you'll see the exact sequence that you see in the McDonald Mountain exposed along Cactus Ridge. It's a basal quartzite, big boulder conglomerate on a rhyolite, which is red rock rhyolite, which is equivalent to the Flying W. Then you got a kind of a thin shale zone in between, kind of a pipestone, and then a very thick, massive or massively bedded, clean looking quartzite, relatively clean looking quartzite in the upper part. And then that's got kind of an angular relationship at the mouth of Shake Tree Canyon. And then there's a rhyolite in between there. And you see that exact same sequence also over at Tonto Bridge. And Rona Cox went out and correlated the section at Tonto Bridge to the section at the mouth of Shake Tree Canyon. And she calls it the Pine Creek Conglomerate. And these units were deposited between 1708 and basically 1701. But it's the same sequence, this thick boulder conglomerate at the bottom, which I think is typical, looks very similar to what you see in the Houdon quartzite at McDonald Mountain, or actually at McDonald Mountain, you may be actually looking at quartzites in the bread pan, but at Sheep Basin Mountain. So there's the jury's still out a little bit on that, but right now I'm comfortable with that sort of a correlation, that there's actually, the thick quartzite along Cactus Ridge was thought to be all dead man originally. They considered it was thrust in from a thick part of the basin, some 7 kilometers to the present day south, and juxtaposed to the typical thickness of the dead man quartzite, which is about 90 feet. But my mapping was able to show that no, it looks like a conformable boundary between that lower quartzite and the upper one, but there's a rhyolite in between them. And when you actually get to the mouth of Shake Tree Canyon, it all curls up and pinches out across the canyon into an angular nonconformity. And in fact, there's huge boulder conglomerates at the lower part of the section, which are probably being dumped off of the edge of a graben there, sheeted dikes just to the north, less than a mile away.
Mike, there's a question from Fred Zorner. Maybe after that, we should wrap this up.
Okay.
How does the metapellite at Four Peaks and the Maverick Shale relate to the Pinel schist?
How does the metapellite at Four Peaks?
At Four Peaks and the Maverick Shale.
Okay, well, the Maverick Shale is older. Okay. We tried to get the Detrital Zircons out of there, and at one point we thought we could get a weak shoulder that suggested that the Maverick Shale and Barnhart Canyon had a maximum depositional age of about 1632. The Four Peaks quartzite itself and the White Ledge Formation are both deposited on volcanic flows dated at 1657. So, it's not much of a stretch to go to extend that over to the Mazatzal Mountains and say that maybe the Mazatzal group itself was deposited maybe sometime after 1660. It's not a perfect, obviously is a big assumption in there, but the quartzites that are considered Mazatzal equivalent in 2 areas are deposited over 1657 rhyolites. So, and then of course the metapellite carries an age of 1580. Now, it's always possible that in some fold somewhere out in the Pinel schist, there might be, these magmatic gap ages. So far, we haven't seen them, but we have measured, collected quartzites out. For example, at just north of Morenci, there's a place called Pinel Point. And I sampled that one, and that has a maximum peak population age of 1657 in the quartzite there. Of course, it's mapped as Pinel schist, which I did actually call the mapper right from the field just to say, why did you call it quartzite schist? But, and then also out of the Southern Galliero Mountains, we collected some quartzites there that also yielded around 1650 age peaks, but nothing really that much younger. So I think that if you did have these metapellites in the core of the synform at Four Peaks. And they were probably deposited out over the Pinal Basin, just like everything else. But they were long inverted and eroded, uplifted and eroded long ago. And now there's a paper by a dissertation by Myra Keep that looks at the inversion of the Pinal Basin, which is a good one to look at as well. But I think the Pinal Basin's been uplifted so much, you've really exhumed a lot of rock.
Very good. Hey, thank you so much for doing this. And I want to thank the audience, those folks who tuned in, for tuning in as well. This has been great. And Mike, I'll get the recording up and at YouTube, and I'll let you know where it's at. And I'll let the community know where it's at.
Okay.
Thank you so much for giving a great presentation.
Great. Well, thanks so much.
Yeah, thank you, Mike. Appreciate it.
Okay, thank you all.
Good night, all.